Here we start with a lecture about signal transmission, and I want to start with a small demonstration. What do I mean by signal transmission? So when we draw a schematic, we need to connect two places in a circuit to bring a voltage, a time-varying voltage from one place to another. So in a schematic, we just draw a line, and then when you do it on your little boards, you take a wire and connect one point to the other. And today we want to discuss a little bit what happens in detail, especially when we talk about fast signals. So the demonstration now is I have a little device here that is a signal generator. It generates this square wave. It's quite nice. It has a bit of a time constant that you see when it rises, but otherwise it's a nice signal, and I just directly loop it back via a few centimeters of cable into a receiver that then displays the signal. Now that's for a short cable. So the next step is I take a little longer cable. So I go from 2 centimeters or so to 10 centimeters. And what you see already is that you still see a square wave, but it has already some features. So if this is a signal transmission, you just want to transmit a binary 0 or 1s, that's not a problem. But if you're interested, for instance, in the precise position of the leading edge, if you're measuring time with high precision, this may already be a problem. So this is what a few centimeters of cable do. Now, as the next step, I can take a relatively long cable. Let's say, what is it, 2 meters maybe. I just plug it in on one end and the other one. Now what you see is pretty bad, right? This is not what you have in mind when you want to send a signal from one place to the other. And furthermore, it really depends on what exactly I do with the cable. So this is not a good situation, and today we will see how to do better. Okay, now I need to switch back. Okay. Yes. So can you see the cursor? Okay. So this is what I meant. Normally, when we looked at schematics, we just drew a line from one point to the other, and we expect this to be an ideal wire. So we assume that at every time, every given moment, the current that goes in on one end is identical to the current that comes out at the other end, and whatever voltage we apply here is instantly brought to the other side, so we have the same voltage here. So these are really ideal connections. So when we draw a schematic and we draw a line between two things, two places in the schematic, this is what we assume. And we've just seen that when you do this with a real cable, it's not exactly the same. And why is this? Because in real wires, you have other effects. You have a resistance in the wire, so it's made of copper typically or something, so the current sees an ohmic resistance, so there will be a voltage drop along the wire. Then when there's a current flowing through this wire, there will be a magnetic field. When the current changes, the field changes, and this will induce a voltage again on the wire, so this is symbolized by this inductance. So every piece of wire has a bit of inductance. And then, of course, there's a potential on the wire, and the surrounding potential may be different. So there's also a bit of capacitance in every piece of wire, okay? So the simple straight line approximation, so the ideal connection does not always apply for real wires. And we also expect that the signal does not propagate instantly from one side to the other. Maybe you heard about the special relativity, that nothing can propagate faster than the speed of light. So it's not really possible that one end does the same as the other end at the same time without any delay. So we expect something to happen. So in general, when we connect two things with a real wire, we expect that the voltage on the other end is not instantly the same as on the input, and the same for the current, because through this parasitic capacitance there will be some current flowing to the to other conductors. So one has to take the whole loop into account. So the wire plus other conductors in its environment. So let's start by discussing a short wire. So this more or less symbolic model of a wire that has these three components: resistor, inductor, and capacitance. Like this, it cannot be appropriate for very long wires, and it can only work for medium size, let's say, wires, not too long, with relatively slow signals. And the applicability is basically limited by the range where this circuit would really behave like an LC resonator. So when you get into frequencies where the resonance here would become relevant, then it's clear that you're stretching this simple picture too far. Okay, then you should start worrying: does it really matter where this capacitor is? Should it be here or should it be there? Should I have several, more than one, and so on? So this simple picture will only work when your signal frequency is much smaller than the LC frequency of this resonator. Then, if that is the case, you can model a wire like this. And it turns out that cuts off something here. It's even worse. Sorry. Let's try this then. So it turns out that the simple picture is only applicable if the wavelength of the signals that you're sending over the wire is much longer than the wire itself. So if you have a piece of wire and the frequency of the signal that you're sending, the relevant frequency, is so high that it would make several oscillations, it's clear that you cannot model your wire with a single circuit. You will have to make a more finely segmented picture of it. So maybe a comment about what is a relevant frequency. Typically what you want to send is not a pure sine wave. So what is the frequency that you're talking about? And what you have to consider then when you design a circuit and worry what is the highest frequency that you need to take into account, and it depends on your application. So when you have slow sensors, then this will be like hertz-like frequencies. When you do audio, then the frequencies you care about in the tens of kilohertz maybe. You don't need to design your circuit to work at many megahertz, because those frequencies will be filtered out later on. So you don't really care what happens at a megahertz when you transmit an audio signal. But when you do radio-like signals, you need to think about megahertz waves, and when you do very high-speed digital, you even need to think about gigahertz. And it's not only the repetition rate of your signal that matters, but it's the speed. So, for instance, if you have very sharp rising signals, then you need to look at frequencies that are of the order of the inverse of the rise time. Okay, so a fast signal requires a high frequency capability of your circuit and your signal transmission. Okay, it's not just the repetition rate, but it's also the rise time of your signals. So if you're doing digital, then the rule of thumb is typically that the frequency that you need to consider is like 5 times the digital frequency that you're working with. So your analog bandwidth that you need to consider needs to be 5 times the bit rate, for instance. So, and then if you do the calculation, for instance, if you have a 10 gigabit digital link, that gives you an estimate of a frequency of about 30 gigahertz, according to this rule of thumb that you need to consider. And the wavelength of this is only a few centimeters. So when you do multi-gigahertz electronics, a centimeter can already be a long distance, okay? So for fast electronics, the problem that I've shown in the beginning is everywhere. For the things that we do here, when you do these exercises, it's usually not a problem. You can just take a wire and connect two pieces, and you see what you expect. Okay. Now, when you have a short wire, which is a few centimeters or not extremely long, then how to actually model that depends a bit on what it's connected to. So it's not always appropriate to use an R and an L and a C. When the signal is very slow or the wire is extremely short compared to the frequencies that you look at, then you simply do nothing. Then you just take the ideal wire. When the wire is connected to something that has a very high resistance, so a high resistance or high impedance terminal, these are most inputs of receivers, for instance, or an output with significant output resistance, then the capacitance is most important. You don't need to consider the inductance typically in those cases. You just model your wire by a capacitance. So this is actually the most common case. When you have very short lines, you need to worry about how much capacitance is attached to that line. And that will give you rise times to your signals. On the other hand, when your short wire is connected to a very low impedance point, for instance, a voltage source or a large capacitance, which is something that you do when you stabilize your power, for instance, or you need a stable reference voltage, then the inductance is most important. That's why when you look at the traces that lead to chips on a printed circuit board, for instance, the power traces are often very, very wide. And that's not so much for the ohmic resistance. It's also for the ohmic resistance, but it's also mostly because a wide wire minimizes the inductance of a trace. So when you stabilize a voltage, or you want to give a stable voltage to a chip or to a component from a place nearby, a decoupling capacitor or something, you normally take a relatively wide trace for that to minimize inductance. And on the other hand, if you have a very high DC current, then it's the resistance of the wire that you care about and nothing else, okay? Okay, but now for the rest of this lecture, we talk about long wires. And in order to describe a long wire where your signal will do many waves, you cannot just do one of these RC, LC blocks. You have to separate your model into finer segments. And for the rest of this talk, or for most of this presentation, this lecture, we will neglect the resistance and just look at systems that consist of inductance and capacitance. This picture of signal transmission along a wire that is modeled only with inductors and capacitors is in this fashion is valid only when the fields that develop around your wire have negligible components along the wire. That is called a TEM wave, so a transverse electromagnetic wave. So all the fields are only in the plane perpendicular to your wire. Then you don't need to model any fields that go from here to there. You just need to do this locally and can do it with these components. And the conditions that need to be fulfilled, so in order to have these TEM waves, is that you need two conductors. Like here we have this cable and some ground plane. And the geometry of this needs to be constant along the line. So if you make a cross-section here and a cross-section there, it needs to be the same. Then this is a necessary condition for a transmission line that can be modeled in this way. If you don't have this condition fulfilled, then the fields will not be strictly perpendicular to the wire. So oops, I went backwards, I think. Yes. So the other condition is that the relevant wavelengths that you're considering must be much larger than the transverse dimension of your conductor. I mean, if you have extremely fast signals, like if you consider going towards microwaves or light even, then it doesn't really care about the fields, the conductors, right? It'll just go through in straight lines and do whatever it does. But if the wavelength of your wave is large compared to the dimensions of your conductor, then the wave is guided by the conductors, okay? So when this is fulfilled, we talk about a transmission line, and we will soon see that there are very good reasons to design your signal carrying wires as transmission lines. In fact, they're almost everywhere in electronics, especially in high-speed electronics. Everything will be designed as transmission lines, following these requirements. Yeah. So the most common types of transmission lines that you will see are the following. So it can be a printed circuit board where you have a conductor on top of a ground plane. So printed circuit boards typically have multiple layers of conductors, and often one of them is like a ground plane with a constant potential, and then a metal trace running in constant distance to this forms a transmission line. So it fulfills the requirements that we had. So this is the simplest transmission line. The other thing that is used not when you're not on a PCB, on a printed circuit board, but really bring wires from one place to another, is a twisted pair of wires. So you just take two wires and twist them around each other, and that guarantees that you have a constant distance, a constant cross-section of this pair of wires along your cable. Maybe when you look at network cables that you use, you'll sometimes see this acronym UTP, which stands for unshielded twisted pair. So these are used, for instance, in network cables. Then another type that you will often see in laboratories, it's used in many places there because they're very convenient and modular, are these coaxial cables, often called LEMO cables, but LEMO is just a manufacturer, of course. Others are micro-coax or SMA cables. So they have a conductor in the middle, and then a metal, usually a copper mesh around them, and in between there's a dielectric that maintains the constant cross-section here, makes sure that the distance between the inner and the outer is always constant. So these three types are the most common transmission lines that we'll see. And in the practical session, you'll also make some experiments with these coaxial cables. Okay, so let's look a little bit more in detail at the model that we're making. So we chop the long cable, the long transmission line into smaller segments or lumps with a length delta x. So we look at little pieces of this, call the length delta x, and here we have one of these segments. The inductance is delta L, the capacitance is delta x, and these delta L and delta C is the capacitance, and delta L and delta C are proportional to the length of the piece. So when you make your piece smaller and smaller, the values that you have here are smaller. So the values for delta L and delta C get smaller when you reduce delta X. So the relevant parameter here is the inductance per unit length and the capacitance per unit length, so L prime and C prime. So these are the numbers that characterize your cable, and then the size of your lumps determines the values that you use here for capacitance and inductance. So let's look at this, for example, for a coaxial cable. The inductance of such a cable can be calculated with this formula. It's proportional to the length. You have the logarithm of the radii of the inner and the outer conductor. So R is the inner conductor, and RO is the radius of the outer conductor. And then in between you have a dielectric with a an epsilon, for instance, of 2 is a typical number. The relative permeability is typically 1, so there are not, I mean, you will not use materials here that have a high permeability. And then mu0 is the vacuum permeability. So this is the formula that you get, and you can, obviously, since it's proportional to the length, you can define the inductance per unit length L prime as this. And if you plug in these numbers here, you typically get numbers like 2 nanohenries per centimeter multiplied by the logarithm of the ratio of the inner and outer value. So with some realistic numbers, for instance, you get a value of 3.2 nanohenry per centimeter. So that's a good order of magnitude to remember. So a piece of wire typically has a few nanohenries per centimeter. We've done this here for a coaxial cable, but this depends only logarithmically on the radius. So when you make it much larger or you change the geometry a little bit, it will still be in that ballpark. So that's just an order of magnitude to remember. Next thing we need is the capacitance per unit length. There's also it can also be calculated if you know the fields around a radial arrangement like this. And if you plug in the numbers here for epsilon and epsilon r of 2, then you get something like this, 0.56 picofarad per centimeter times this combination of the relative dielectric constant and the logarithm of the ratio of the radii. And then again for the same numbers, so we're looking at the same cable as we did for the inductance, you get a value of 0.7 picofarad per centimeter. Okay, so this was for a concrete example of a coaxial cable, but normally when you have a piece of wire somewhere, you also typically get something like a picofarad per centimeter. Just an order of magnitude to keep in mind. So we'll later use these two values to do some simulations. Okay, actually we'll do it right now. So this is the circuit that we'll simulate. So it's a model of this transmission line where we have a large number of these segments. So we take segments of 1 centimeter. So mentally, I mean, we in our mind, we chop our cable into pieces of 1 centimeter length. The cable has 50 centimeter total length, so we have 50 such pieces. And we calculated the inductance. So every inductor here is modeled by 3.2 nanohenry, and every capacitor is modeled by 0.7 picofarad. So this is the SPICE deck that was used to run the simulation. I think Georg introduced SPICE a little bit. So normally you use SPICE from the GUI, which is fine and works very nicely. But sometimes it's actually useful to write these SPICE decks yourself. If you wanted this in the GUI or later with a much higher number, then you have to do a lot of click and point. While something like this you can write with a Python script and then just execute it. Quite nice. What I do here is I simulate a step pulse at the input. So it goes from 0 to 1 volt with 0.1 nanosecond rise time and 0.4 nanosecond width. So, and then we look at what happens in a transient analysis that runs in 0.1 nanosecond time steps for 5 nanoseconds. So this is what this SPICE deck means. Now we look at the result. So we look at the voltage in 2 places. One is close to the signal source, and the other one is close to the end of the chain. And what you see that here at the beginning, you see something that is basically the same as you put in. And then after 50 centimeters, the signal looks pretty much distorted. You can still sort of measure the propagation speed, so the time here, it's probably difficult to read, but the time delay between here and there, if you look at the axis, is roughly 2.5 nanoseconds. So we can estimate the propagation speed here to be 15 centimeters divided by 2.5 nanoseconds, and that gives you 2 times 10 to the 8 meters per second. We have some shape distortions here, but we'll soon see that these are not real. These are actually an artifact of the discretization. Remember that we said this only works when we look at time scales that are much slower than the LC time, but the LC time of such a block is 0.3 nanoseconds. And since we look at a signal that rises in 0.1 nanosecond, we can't expect this to work. So what we have to do is to go to a finer segmentation, because this model is too crude. It will not describe the propagation of the fast components of the signal properly. So the next slide then has the same thing, but not with segments of 1 centimeter, but of a millimeter length. And now you see that the result after 50 centimeters already looks much better. So now we have per block 1 millimeter and 1/10 of the capacitance and 1/10 of the inductance. So you can still measure the signal shape, and it comes out the signal velocity, the propagation speed, and it comes out almost the same. So the next step then would be to go to infinitesimal blocks here, but we will not do that in simulation, but analytically, of course. And surprisingly, this can be done. So let's start with the analysis of the LC chain. So we look at okay, I have to get used to this. Sorry. Let's look at this node here and the currents that flow in and out. So we start with the capacitor current through this capacitor, and it's given by the capacitance of this little capacitor, delta C, multiplied by the time derivative of the voltage at this node. Okay, that's the usual characteristic of a capacitor. Then the next equation that we need is the current conservation in this node here. So the incoming current is the sum of the capacitor current plus the outgoing current. Okay, or if we write this differently, so the difference between the outgoing and the incoming current is the capacitor current with the minus sign in the sign convention here. Okay, so this is the equation that we need, the Kirchhoff equation. The last thing, then we can already here replace the capacitor current by this equation. So we have the difference between the currents in the two nodes is minus delta C times the time derivative of the voltage at this point. The next equation we need then comes from the characteristic of the inductors. So the voltage across the inductance, for instance here, from between these 2 points, is given by the inductance and the time derivative of the current that flows out here with the minus sign because of how we arrange the voltages here. Okay, so this is in principle all we need to characterize the system. If we take these two equations for every node, for every little block, then we have 2n, for n segments, we have 2n coupled differential equations for 2n unknowns, which are the currents and the voltages in these places. So this is in principle a solvable system of equations, and the numerical solution is what SPICE does. But now we want to do something else. We want to convert this into a wave equation. So to do that, we need to relate the index. So we want to go from indexing points to positions in space. So the position in space is, of course, a multiple of delta x times the index. So this we do here. So this is the same equation that we had. Now we replace again delta C by delta x times C prime and divide by delta x, and then this gives us the difference of the currents divided by delta x is on the right hand side minus C prime times the time derivative of the voltage in this node, and then similar for the second equation, replace the difference of voltages by sorry, the difference of voltages is still there. We replace delta L by L prime times delta X, divide the whole equation by delta X, and then we get this equation here. And I think you already see where this is going. This will become our spatial derivative, okay? So the next thing we do is we replace these all these different functions in and un by continuous functions of space and time, okay? This is done here. So so instead of writing in of t, we write I of x and t evaluated at x equals delta n, x equals n times delta x, and correspondingly for all the others. So in one, if it's I n plus 1, then it's I of x plus delta x, and the same for the voltages, okay? Then if we put this into the equations that we had on the previous slide, then the result looks like this, and this is then already clear that this will become a derivative. So if I now take the limit of taking delta x to 0, then here I have the derivative of the current with respect to the x coordinate. Here I have the derivative of the voltage with respect to the x coordinate, and here I have the derivative of this with respect to time, of course. Now here it seems like a problem, because here I have the current at x plus delta x, but since we let delta x go to 0, it doesn't matter, so this is also the derivative at x. So now we have a pair of coupled partial differential equations for I of x and t and u of x and t, okay, which is equivalent to our set of 2n equations, discrete equations, but now expressed in the limit of delta x going to 0 as a partial differential equation. Okay, and this pair of differential equations has a name. It's the so-called telegraphus equation, and it was first found by Mr. Heaviside himself in 1885, who was a pioneer of electrodynamics, really. And he studied the technical application really for sending signals over telegraph lines in those days. So what we typically do is we decouple these two equations by taking the time derivative of the first one and the space derivative of the second one, for instance. You can also do the other way around. So if you take the time derivative here, you have a mixed derivative of I there, and if you take the x derivative on this side, you have the mixed derivative of I on here, which you can insert, and you can insert this one into this, and what you get is a second order equation for the second derivative of the voltage with respect to the place multiplied by L prime times C prime. The minus cancels here, so we have a plus here. And then you also have the second derivative of the time. So if you take the time derivative here, you have the second derivative, and if you take the x from the x derivative here, you get the second derivative here. So this relates the second derivative of the voltage at a point and the with respect to the space coordinate and the second time derivative. And this is, I don't know how many of you are physicists. So when you're a physicist, you've probably seen this equation. This is a wave equation. It's a one-dimensional wave equation. And then you can go and solve these wave equations in terms of sine waves and so on, but that's not what we're mainly interested in. We don't want to really know what happens when we send sine waves over this, although it can be done like this, but we'll do something else. We'll simply note that any function that has this form, so the voltage u of x and t is some single argument function where the argument is x plus or minus velocity times t, where the square of velocity is 1 over L c squared, 1 over L prime c prime. So every function that is of this form is a solution of this equation. You can easily see that when you plug it in here. So the second derivative with respect to the space is the second derivative of the function, and the second derivative with respect to the time of this is v squared times the derivative of the function. Okay, So it's clear that this is a solution of the equation. And this simple fact has a number of remarkable consequences. So a solution like this means that a signal shape, f, propagates along the transmission line with a constant velocity given by v. Okay, so and then here I write plus or minus. Both are solutions of the equation because when you do two derivatives, you get voltage squared, so you also get the sine squared, so plus and minus are solutions. So the ones where you have the minus sign propagate to the right, from the left to the right, and the ones where you have a plus sign propagate from the right to the left. Okay, so these are solutions where a waveform is travels unchanged along the wire. Okay, it has some properties like it's a linear equation here, so the voltage only appears linearly. So every solution, every sum of two solutions is again a solution of this equation. That's the superposition principle. So you can, whatever wave you have, they can add without disturbing each other. So this is also valid for waves that run in opposite directions. So two waves, one traveling left to right or one traveling right to left, they can just go through each other and they do not disturb each other. Okay. So when they pass each other, you have the same signal that came in from the left and the one that came in from the right on the other side. The other remarkable consequence of this is that this behavior is independent of the signal shape or frequency. So you don't see any dependence here of the signal shape. So this is true for any signal. And the fact that it doesn't depend on frequency, there's no explicit frequency in this, is sometimes called there's no dispersion. So all frequencies are transmitted with the same velocity and the same attenuation, or no attenuation actually in this case. So in summary, these transmission lines that have that fulfill the requirements that we listed, so that we have two parallel conductors with constant cross-section, they have ideal transmission properties. Okay, so that makes them very useful, and that's why we will see them everywhere. Okay, so we can try to understand a little more in detail what happens when a signal now passes through such a chain of LC elements. First we look at a signal propagating to the right. So this is it's a solution of this form. And so F is this blue shape here. It is zero outside a certain region and only positive or only non-zero in a certain region that covers several blocks of this model. And then the whole thing is traveling from left to right. And then if you look at the currents here, then in the region where the signal is rising, here the signal is rising, you have a current going down through the capacitor, so the node goes up because there's current going into the capacitor, lifting this point, and then this current flows through the inductors on this side and or through the return on the other side, and discharges again the capacitors on the other end of your wave. So it's like a caterpillar rolling along your transmission line. The same thing when you have a signal that propagates from the right to the left. So the propagation velocity is here. The current now flows in this direction. Again, you have charging the capacitor here and discharging the capacitor there. If you look at the currents at a certain point, they change with the propagation direction. I think that's obvious from this picture, and it plays a role when we look at what happens when we do reflections and terminations. But it's important to keep in mind that the current is always in the direction of the propagation. Strictly speaking, the LC that I've shown here is two cores. You would have to draw it properly, you would have to have several of these over the rise time of your signal. Otherwise, this wouldn't model this kind of signal. So a good model would need several of these LC segments over the rise time of your signal. Okay, let's estimate or calculate the propagation speed in our coaxial cable, we found that the velocity in a transmission line is given by 1 over the square root of this product. So we plug in the numbers or the formulas for L prime and C prime, and we get this expression. And the interesting thing is that the geometry factors, so this logs of the radii cancel immediately. So does this 2 pi factor. And all you're left with is 1 over the square root of the dielectric constant and the permittivities. Now, 2 of these factors have nothing to do with the cable, these epsilon 0 and mu 0. They are just constants of nature. And this particular combination of these constants is known as the speed of light in vacuum. Okay? These 3 times 10 to the 8 meters per second. So by using this constant, we can now write the speed of the signal as c divided by the square root of mu r and epsilon r. This is a universal feature of these transmission lines. Here, in this case, it does not depend on what the dimensions of this coaxial cable actually are. Okay? It just means you have a transmission line, then with some dielectric between the conductors, then you'll get this expression for the propagation speed. So, like I said, we've shown this here for a coaxial cable, but it comes out like this for every type of transmission line. So when every combination of parallel conductors gives you this result. And for typical transmission lines that you will find, this mu is 1. There are no dielectrics with a significant permeability. And this dielectric constant, the relative dielectric constant, is typically in the range between 2 and 4 in practical cases. So this means that your propagation velocity in transmission lines is typically between 0.5 and 0.7 c. Okay, so this is something you can expect if you now do this for what we use in our SPICE simulation. So we take this 0.7 picofarad per centimeter and 3.2 nanohenry per centimeter again. Calculate this. So take these units. So a henry is a volt second per ampere, and a farad is 1 ampere second per volt, or a coulomb per volt. So the units here match. You get everything cancels here, the amps and the volts, and you get second squares over centimeter squared, or which we convert into meter squared. So L prime times C prime is 2 times 10 to the minus 17 seconds squared per meter squared. So if you take the inverse and the square root, then this comes to 2.1 times 10 to the 8 meters per second. So this is 0.7 C, as you expect from our formula. Okay, and this is what we also measured in the SPICE simulation, if you remember. Okay. Okay. So yeah, before we start talking about complex impedances, I think we take a break now. Do you have questions? No? Okay. Great. Then we have a 15 minutes break.
nicht schlimm, aber vor allem die ersten paar Folien, da hast du rot gemalt auf einem bräunlichen PCB, das hat man eigentlich fast nicht gesehen.
Dann schließen wir mal das jetzt an. Okay, so welcome back. So there was a very good question in the break. The question was whether the distortions that we saw in the wire that I've shown were somehow related to the distortions that we've seen in the simulation with insufficiently small blocks, and the answer is no. If you go to really infinitesimal small LC segments, then the transmission on a transmission line would be without any distortion, would be perfect, okay? The reason that we don't see that here is that this is not a transmission line, because there's no second conductor that allows a constant cross-section along the path of the wire. This is completely undefined inductance and capacitance, and it changes along the cable. So this is just not a transmission line. That's why the transmission is not perfect. If you do the same thing with a coaxial cable, you would get perfect transmission. Okay. So this point is important. Okay. So before the break, we looked at the transmission speed, the velocity of signals propagating along the transmission line. Now we'll look at another important property of such a transmission line, the so-called impedance. So we can try to calculate the complex impedance that this network here represents. You remember that we can represent every capacitance by a complex impedance 1 over I omega c, and for the same correspondingly for the inductors as I omega L. So when we have a network like this, we can assign a complex impedance to this Z of omega. So let's try to calculate that. And the trick here is that if you take this chain and you add one more element, so this is an infinite chain, and we add one more element, making something that is already infinitely long a little bit longer shouldn't change the value. So these two circuits should have the same complex impedance. Okay, it's just a small trick that we use instead of trying to add up an infinite sum of these elements. And the last part that we have here is now the same as we had originally. So we can replace this one by this circuit, and then we still expect the left-hand side to be the same as the right-hand side. So this is shown here. So the complex impedance on this side, which is a parallel of this Z and the delta L and delta C element, should be the same as the original Z of omega. So, or in terms of a formula, this is here. So Z equals ZL, so the complex impedance of the inductor, plus the parallel circuit of the capacitor and Z again. Okay? We're just using a fact that it's infinitely long. Okay, so again, this is the same equation repeated, and the parallel circuit is the parallel of two impedances is given by this expression, so 1 over ZC plus 1 over Z to the minus 1. We multiply the equation by this term, then we have, and bring this one to the other side, so here we have Z minus ZL multiplied by this term, and then what's left on the other side is 1. And so we multiply this out, so you have Z divided by ZC minus ZL divided by ZC, then this one is Z divided by Z, which is a 1, and you have minus ZL divided by Z of omega. So the 1 here cancels with the 1 there, and you multiply with Z again, and then you have this quadratic equation, Z of omega to the squared is minus Z times Z minus ZL times ZZ is 0. Okay. Now we rewrite this again, putting in the expressions for the complex impedance of the inductor and the complex impedance for the capacitor. And that gives us this equation, so Z squared minus this is equal to that. And in this ratio here, the delta x will cancel. while here it remains. So when we now go to infinitesimally small delta x, this term will disappear, and all that's left is this term, L prime over C prime and Z squared. So since the sum is 0, we know that the complex impedance of the whole thing is the square root of the ratio of L prime over C prime. Okay? And this is called the characteristic impedance of the transmission line. So there are there's a remarkable effect that this is a real number. So we started out with complex impedances. We have Zs for the complex Zs for the individual capacitors and the individual inductors. But the infinite chain turns out to have a real impedance. So it's not complex, it's real. And it's independent of the frequency. So we started out with elements that have frequency dependence in their impedance, and the result of the infinite chain is that it's independent of the frequency. It's also independent of the cable length. Of course, we worked with an infinitely long cable. Right, and it means the fact that it's real means that current and voltage have the same shape, depending on whether we're right going, left going with different sign. But the current is simply 1 over this characteristic impedance multiplied by the voltage with a minus sign for the left going. Okay, there's no frequency dependence and no phase change. Okay, let's do this for the coaxial cable. We plug in the formulas that we've shown earlier for the impedance per unit length and the capacitance per unit length. Again, here some terms. No, this time the terms do not cancel. Sorry, and we get some factors that are independent of the cable and some that are dependent on the cable properties. So we have the square of the logarithm in the square root, so we pull it out of the square root. This factor that is independent of the cable properties turns out to have the unit of resistance, and it's called the impedance of free space. It's not terribly significant. It's just a combination of constants of nature. So for this one, in most cases, we have mu r equal to 1. So we can also neglect this one, and all we need to consider is 1 over square root of epsilon r multiplied by the logarithm of the ratio of the radii. And here we have the 376 ohm divided by 2 pi is roughly 60 ohm. So the rule of thumb for the impedance of such a cable is 60 ohm divided by the square root of the relative dielectric constant multiplied by the log of the ratio of inner and outer radii. So this can vary a bit, and you can affect it with the geometry of your transmission line. But typically, it comes out to be somewhere between 30 and 100 ohms. So again, this is only logarithmically dependent on the dimensions, so you cannot make it explode really. So you're kind of stuck with values in this region. And the most common value that you will find in very many cables is 50 ohms. So these are the so-called RG58 cables that you'll often see in laboratories, the LIMO cables. They usually have 50 ohms. Antenna cables for home installations, I think, have 60 ohms. But it's always in that ballpark. Okay, so this brings us to the next important point, and this is the one statement. If you forget everything else from this lecture, this is the one statement that you need to remember and understand. An ohmic resistor with the value of this characteristic impedance looks exactly like an infinite transmission line. Okay, this is the thing that you should really understand. So if you have a long transmission line that is infinitely long, you can as well terminate at some point and replace the rest of the infinitely long transmission line by a resistor. This is called a termination. Okay, so when you have a transmission line of finite length, you can simply put a resistor of 50 ohm at the end, and it'll behave as if it was an infinite transmission line. Okay. There's an interesting question here raised by the fact that this LC chain behaves like an ohmic resistor. There's a fundamental difference between resistors and capacitors and inductors in that a resistor generates heat. So when you have a current flowing through a resistor, it dissipates the power. So it takes power out of your circuit and produces heat instead. Okay? While a capacitor and an inductor don't do that. They have pure imaginary impedances. So they only store energy temporarily and give it back later. So they don't dissipate energy. So the question is now, if you have a circuit that consists of only elements that cannot dissipate energy, how do you get in the end a circuit that appears to dissipate energy? And the answer is, of course, that we took it to be infinitely long. So when we insert some energy at one end and we make it infinitely long, it can just propagate to infinity. So these elements, although these elements never burn the power, it looks like it burns power because it just goes off to infinity. So the question is now, when we have a finite chain, a chain that ends at some point, how does that behave? We cannot have the same thing here. Something must happen because the energy must go somewhere. And so we look at the simulation again that we had in the beginning with this element, this thing with 500 elements. So we make it longer now. We make it 1,000 elements. And in the simulation we only looked at this point here, at this part. So we put the signal in, and it comes, and we observe it after 50 centimeters, and it's almost perfect. Okay. But then if we let the simulation run longer, something funny happens. If you look at the voltage here, you see the pulse a second time. And a little later, you'll see it once more, but this time with an inverted amplitude. Okay, so something is happening here, and this is called reflection. So what happens is the following. The pulse starts here. After once or half the traveling time along the full chain, we observe it in the middle. Then it goes here, is reflected, comes back. We observe it again after twice this time. And then it goes back here, is reflected again, and we observe it here. The difference is that this time, when it's reflected here, there's a sign flip. While on this end, there's no sign flip. And then we'll in the next pages look at why this is different. Okay, so yes. So we have different boundary conditions at the two ends. So on the left-hand side, at the left-hand side, we have a voltage source. So here, when the signal comes back, we fix the voltage to 0. So this voltage source gives one pulse, and then it's fixed at 0. So our boundary condition here for our wave is that the voltage is 0, while on the other end, we have instead nothing. So there's no current flowing here, flowing out. So the boundary condition at this end is that the current is 0. This is called a fixed end when we fix it to some voltage, and this is a free end when we just let it dangle in the air and let no current go out. And to make things easier, from now on, we will no longer do these simulations of LC blocks, but we use perfect LC chains. There's perfect transmission lines. There's also in SPICE a symbol, an element for transmission lines. So you can really simulate perfect transmission lines in SPICE. You don't have to use this. Okay. So let's look at the reflection of at a fixed end. So we have a signal coming from here, and we fix the output at the end. So the voltage is constant here, but there's no constraint on the current. So the signal coming in at the reflection point is given by the shape of our traveling wave. So we have a wave traveling from left to right, so it's a x minus vt. Now we make an ansatz for the voltage at this point here, And the ansatz is that we assume it's a superposition of a left-going and a right-going wave. So I mean, we do this because we kind of know what's the result. We take the right-going wave, which is the incoming, and we add a left-going wave like this with a different shape. We say it can have a different shape. And now the boundary condition is that the voltage is 0 at that point, which means that the left-going and the right-going should be the same with a minus sign here. And you can, so the boundary condition is at this place. You can make a change of the variables, and you come to the conclusion that the left-going waveform is minus the right-going waveform at a different time, but it's the same shape with a minus sign. Okay, so we can model the situation of a wave coming from the left to the right to this point where the voltage is 0 by adding another wave coming from the right, which exactly cancels the incoming wave at the reflection point. Okay, and then this cancellation is the same as saying the voltage is fixed. So this reflected signal has the identical waveform. It is mirrored, so it's flipped. Oops, yeah. Okay, yes, we show the picture here already. It's flipped. It is inverted in amplitude. Yes, and then the only comment I wanted to make also is if we don't reflect at ground potential, at 0 potential, you can also reflect at a constant potential. Then the reflected voltage is offset by this potential. Okay. But let's look at graphically what it does when we have this reflection. So you have before reflection the incoming waveform here, traveling from left to right. There's our invented second wave that comes from right to left. So this is not real because this part of the wave of the transmission line doesn't actually exist. We just treat it as if it was there. Okay, and then these two waveforms arrive at the reflection point, and we design them such that they cancel exactly at the reflection point because this is our boundary condition. Okay. We know it's a solution to add these two, and this solution fulfills our requirement. So what we have after the reflection is that the incoming wave, if this was a real transmission line, would go to the right, but it's not there. The only thing that's left is the one that's coming from the right, now traveling in this direction. Okay, so we have a reflection at the fixed end, and it creates a mirror image of the incoming wave and with the inverted amplitude. Okay, similarly we can treat the reflection at the free end. So there's no voltage constraint on the other side. The only constraint is that we say there's no current. So again, we assume that the full solution is a superposition of the incoming and an outgoing wave. But now the boundary condition is that the current is 0, so it's -1 over z. And then we have a sign flip here because, like I said, the current for a left-going wave has a minus sign with respect to a wave that's going right. Okay. So now this boundary condition leads to this, that the left and the right are the same with a plus sign, also mirrored again at the reflection point. Twice the reflection point, but without a sign flip. Okay. So what does it mean graphically? So again, the same situation. We have the incoming wave. Here is our boundary, and the imaginary second wave that's coming from the left. Then at the reflection point, the currents, which are represented here by the red arrow and the blue arrow, exactly cancel. So this one carries a current flowing from left to right, and this one has a current flowing from the right to the left of exactly the same magnitude but opposite sign. So they cancel exactly at this point. What does not cancel is the amplitude. So while they are going through each other, the amplitudes add. So what we see here is actually twice the amplitude of the wave during the reflection. But after the reflection, we see the image of the incoming signal going to the left. Okay. Does that make sense? Good. Okay. Now, what happens if we do not have a free end or a completely free or completely fixed end, but instead we put a resistor here, some value? Now the boundary condition is now Ohm's law. So it's voltage equals resistor times the current. So again, the same ansatz, left going plus right going. Then the current is 1 over Z times the left going plus, so it's minus 1 over Z plus of the left going, and plus 1 over Z times the right going, because the sign flips when the direction flips. So if we insert this into our boundary condition, that voltage is resistance times current, we get this equation. And then if you sort the terms for left and right, you get something similar, but with different factors. So here you have Z plus R, and here you have R minus Z. So the left-going wave that we now need to assume to get the proper behavior at the boundary condition is R minus Z divided by R plus Z multiplied by the incoming wave. So, and this ratio here is called the reflection coefficient. So the amplitude of the reflected signal when we have a resistor at the end is given by this expression. Okay. This is just repeated here. So this reflection coefficient, if you put in values for R, it can only be between -1 and +1. Minus 1 is of course what you get when R is 0, and +1 is what you get when you have an infinite resistance. And the amplitude at the termination is given by this expression. You can again add the incoming and the outgoing wave, and then you have 1 plus this reflection coefficient times the amplitude of the incoming wave. Okay, so the amplitude of the reflected signal. What was I trying to say here? I don't remember. Anyway, so the different cases of this equation include what we had before, the fixed end and the free end. So for R equals 0, we have a fixed end, and the reflection coefficient is -1, and 1 plus the reflection coefficient is 0. When you put in exactly the termination, the characteristic impedance, then the reflection coefficient becomes 0, which is a very nice property, which we should have expected, because we said before that an infinite transmission line behaves exactly like this ohmic resistor. So when we have this ohmic resistor, there's no reflection, and the amplitude at that point is simply the incoming amplitude and nothing else. When you have the reflection at the free end, we had that before, the reflection coefficient is 1, so the amplitude is not inverted, but the amplitude at the transmission point is twice the incoming amplitude, okay? And if you have something that is in between, so when you have a resistance that is larger than Z0 but not infinite, then your termination is too soft. So a large resistor is like a soft termination, and it's too soft when it's larger than the characteristic impedance. So you get a partial reflection. So part of your signal is reflected, but you still see a bit of an excess of your signal. While on the other hand, if the termination is too hard, so you make a too small resistor here, there's also partial reflection with a negative sign, and the amplitude at the reflection point is less than 1. Okay. Now, what does that mean in practice? How do you terminate your signals? So let's say you have a signal source here, and you have a transmission line, and you have a receiver on the other end. The receiver is like an ideal amplifier. It has no input resistance. So what you need to do, if you want to send a signal cleanly from here to here, you take your transmission line, and you put a resistor here to ground, which has the resistance of your characteristic impedance. So if it's a normal LEMO cable, you put a 50 ohm termination resistor here. You will do this in the practical exercise and see what that does. So this is the cleanest solution that people usually use. So you have your signal, your cable, and at the end you put a termination resistor that connects the center of the coaxial cable, for instance, and the outer shield of the coaxial cable. So these termination resistors are either external resistors that you have to supply yourself, or they're often integrated into your receiver, or they're even selectable. If you look at your oscilloscope, there's often a button where you can switch on a 50 ohm resistor that is then added to your input, which is meant to do just that. So when you plug in a coaxial cable into your oscilloscope, and you have to turn on the 50 ohm resistor to give you a proper termination. Okay. So when you have more than one receiver, then this termination has to be only at the end of the bus. You cannot terminate at multiple places. That will give you reflections or attenuation. So what you do when you have one transmitter and several receivers, you let the signal start in one place and then have receivers along the line that do not terminate, and only at the end of the line you terminate. So you want the signal to propagate all the way along your cable and only terminate it in the end. Okay, so this is a nice solution. It's very clean, but it's not always possible. So there's an alternative, which is to terminate at the source. So you put a 50 ohm resistor now in series with the signal where you insert your signal. So now what happens is two things happen. First of all, the input amplitude is decreased by a factor 1/2. So on the cable, you only see half the initial amplitude that you would have without this resistor. However, when you have no termination at this point, we know that from the reflection at the open or at the free end, you have a doubling again of the amplitude. So the receiver will actually see the original amplitude. So it doesn't make a difference. So you can also do it this way. The only problem, if it is one, is that the signal now travels along the transmission line, comes back, and is absorbed only when it comes back by this termination resistor. Okay, so that's perfectly fine if you only have one sender and one receiver. You can do it like this. What many people do, however, is also to terminate at both ends. In that case, you see an overall reduction of the amplitude by a factor 2. So then the receiver will see only half the amplitude, because you decrease it here by a factor 2, and you don't get it back from the reflection coefficient at this point. So you need to be able to afford this loss of amplitude, but it has the advantage that any reflection or any imperfection that happens along the line will be absorbed quickly at one of the ends of the cable. If you don't have that, and you have, for instance, a connector are typically sources of reflections, because they change the impedance of the cable. So there can be a part of the amplitude can be reflected at the connector, and then it goes back to the source, where it is, in this case, for instance, when you had a connector in the middle, the signal goes out, is reflected here, and it comes back, where it's reflected then again, and then later it arrives as a distortion on your receiver. So this can be avoided when you have this termination on both ends. Okay, so sometimes people do that because it helps keeping your system clean. Okay, let's take a look at some examples. So for instance, we have a signal source which has a certain output impedance, 450 ohms in this case, and we insert a signal into a transmission line with 50 ohms and a propagation delay of 1 microsecond, and send a signal then to a receiver where we have no termination. So of course we know already that we will expect some reflection here, but what does it mean? We assume we have a pulse height from the source of 10 volts, and then this is reduced at this point here to 1/10 because the 450 ohms and the 50 ohms of the receiver of the transmission line form a voltage divider. Okay, so this is like driving a voltage divider of 450 to 50, and so what you see here is in the end only 50 ohm divided by 500 ohms, so it's 1/10 of the incoming voltage. So here you have a pulse of only 1 volt. So this will travel down the line, and you have a reflection at the free end because we have no termination in this case. So the signal will come back with a reflection coefficient of +1 to the source, where it will be reflected again. But now the reflection coefficient is given by this formula that we've derived before. So it's the difference of the two resistances divided by the sum. So it's +0.8. So here we have a reflection coefficient of +1, and here we have a reflection coefficient of 0.8 because this is not the correct termination value. Okay, so then something interesting happens when you follow that for a while. So let's see the input makes a step function, goes from 0 to 10 volts. So which means that the input of the cable goes from 0 to 1 volt, and this then travels along the cable. So this is basically as a function of space shown here. So this is the x coordinates. You see that how the voltage propagates. So the step propagates along the cable, and at some point it'll reach the end. So this shows then as a function of time here at some point in the middle of the line the voltage. So if you have an oscilloscope in the middle of the line, it'll see a step of 1 volt at this point. And this here is now showing, so to speak, the voltage along the cable. Now after 1 microsecond it reaches the point here, is reflected, and the reflected value comes back with a positive sign and adds itself to the incoming. Okay, so since the incoming is still there, what we see is not a step here, but we see a step on top of a flat value. So so this wave is now traveling backwards and is added to the 1 volt from the first level. Okay, and when it reaches the point in the middle, then we see the second step here of the same height there. Now, eventually, after almost 2 microseconds, it'll reach the incoming point, and here we have a reflection again with a positive sign, but the reflection coefficient is not 1; it's only 0.8. So now the height of the step is reduced from 1 to 0.8. But since the incoming step is still on, it adds to the original one. So this travels back, and we'll see a smaller step after some time when we look at it in the middle. And this will continue several times, and each time it's reflected here, the step size becomes smaller by a factor of 0.8. So when you look at the oscilloscope in the middle of the line, for instance, you will see a series of steps that get smaller and smaller. Okay, and so this is interesting because it's a model for a very short transmission line. So what happens when you have a very short transmission line and you don't terminate it? So this is what you actually do when you don't really design a transmission line. You just have a short cable that happens to be on top of a ground plane. You don't want to think of it as a transmission line. You just want to think of it as a short piece of cable. Okay. And now, if you run this for a long time, this is a simulation, then the result looks like this. And maybe this curve looks familiar. So you see a series of steps, and the steps get smaller and smaller. Okay. And now, if you don't look very close, you don't see the steps. You just see this curve, and this curve is exactly the curve that you see when you charge up a capacitor through a resistor. Okay. So a very short transmission line that is not terminated behaves exactly like a capacitor that you load through a resistor. So there's no inconsistency here when we say a transmission line. Everything is a transmission line, and it behaves perfectly. So why does a short cable behave like a capacitor? And this is the answer. When you really look at what happens, a short transmission line will look like a capacitor. Okay. Another thing that sometimes happen is that you connect two cables and the two cables don't have the same characteristic impedance. This is normally not wanted, but sometimes it happens because the impedance is not always perfectly under control. When you come with your cable and plug it into a PCB, then the traces on the PCB might not have the same characteristic impedance as your coaxial cable, for instance, because the dimensions were not perfectly matched, or the dielectric constant may be slightly different, and then you get a different value for the impedance, and then you have the situation like that is shown here. You have one transmission line with one impedance and another transmission line with another impedance. So let's first consider a right-going signal. So we have a signal source here that sends something into this transmission line, and then we look at what happens here. And in order to understand what happens here, we replace this setup simply by a termination resistor. But we terminate it with a wrong resistor. So we know what happens when we have the wrong resistor here. We have a reflection, and this is the reflection coefficient. Okay? So the first thing that happens when you have an impedance change is that a part of your wave will be reflected back. The other thing that happens is, of course, that the part that is not reflected back will travel on in the second transmission line. So this point here acts as a signal source for the rest of your transmission line. So the amplitude that you have then traveling down the second point, the second line, is the sum of the incoming and the reflected, which is R times the reflected, or 1 plus R times the incoming, sorry. And this combination of 1 plus R is called the transmission coefficient, okay? So you have a reflection coefficient, and 1 plus R is called the transmission coefficient. So you have part of the signal being reflected back, and another part travels on in the second cable. This is shown here now for a numerical example. You have a signal source back terminated with 50 ohms. You have a 50 ohm cable, and then you come to a PCB, for instance, where your trace impedance is 100 ohms. But you terminate properly the 100 ohms, so you don't have reflections there. Still, the incoming signal, if you observe it here, you will see the following. The incoming signal is reflected back, and you'll see it again with a reduced amplitude. So this, the reflection coefficient is 1/3. So 1/3 of the amplitude comes back to your source. But the rest of the signal, so 1 plus 1/3, travels on. So here you have the amplitude of a higher amplitude actually than on the incoming signal, traveling along the second line. And if it's properly terminated here, there's not really a problem. So the signal arrives, but it arrives with a different amplitude. And if the reflection to this end is not a problem because there's no receiver there, then it's fine. But still, yes. So this is the transmitted factor 4/3. The transmitted is larger than the incoming. This is interesting, and you can wonder how can I increase the amplitude by doing this. I mean, after all, you would expect it should become smaller because part of the signal is reflected back. So how can the signal that travels on be larger than the incoming? Doesn't that violate energy conservation? No, it doesn't. Because you have a higher impedance there, the power carried by the wave is different. So the power carried by a wave is, the instantaneous power is voltage times current. So for the incoming original wave, you have voltage squared divided by the impedance on the first transmission line is 5 milliwatts. Then for the transmitted wave, you have 1/3 of that, 4/3 of that, squared divided by the impedance of the second, which is 100 ohms. So the power here, although the amplitude is larger than the incoming, is actually smaller because the impedance is higher. Okay, so higher amplitude does not mean more power because the impedance is lower. Then if you calculate the power of the reflected pulse, you get this 0.5 milliwatts, and this of course adds up to the initial 5 milliwatts. So there's no problem with energy conservation here. Okay, you can also have a transition to a lower impedance. So if you come in with a 50 ohm cable from the left and continue into a 25 ohm cable, then what you will see here is that the reflected signal actually has a negative amplitude, and this time now the transmitted signal has a smaller amplitude. Okay, still the conservation of energy will still hold, but in this case you have a smaller amplitude later. So in general, you want to avoid such impedance jumps. So when you design your system, you should be careful to never do that, because if you don't have proper termination of the signals at all places, or you have multiple listeners, then these reflections usually cause problems. So so whenever you can, you should avoid impedance jumps. So that's an important work of the designers, to make sure that along a transmission chain that typically goes through several steps, cables, PCBs, other cables, the characteristic impedance of the transmission lines doesn't change. It's always the same. But sometimes it's not possible, and then you have to do something. And one simple thing to do is to add impedance matching circuits. So again, if you have a signal with traveling along this line coming from the left, and the impedance here is larger than the impedance on the right-hand side, you can actually see very easily that if you want this one to be a perfect termination for this one, then R1 plus Z1 need to be exactly the characteristic impedance of the first one. Okay, so if you choose R1 to be the difference of the two, then there will be no reflection, but you will see a loss of amplitude. So there's a certain damping, which turns out to be given proportional to the ratio. So, and there's also a damping of energy here. So because this resistor really burns some of your energy that you have in your waveform. So if that is not acceptable, you need to do something fancier. But in many cases, it's enough to just put a resistor here, and you will see that there's no reflection and the signal just goes through, only changing the amplitude. The bad thing is that this only works in one direction. If you look from the other side, then this cable sees the impedance R1 plus Z1. So that is not a proper termination for Z2. Okay, so this simple single resistor termination only works in one direction. If you need bidirectional matching, you need to do something else. Either you take a different, if you take a different value, you can make it match for the one that comes from the right. But with the combination of two resistors, you can actually find something that works for both directions. Okay, so when you choose the values here properly, you can make this end, so the parallel circuit consisting of Z2 and R2 in series with R1 has to match the impedance Z1, and vice versa. So when the circuit that has Z1 plus R1 in parallel with R2 has to match Z2. Now you have 2 degrees of freedom, and you can make it match for both directions. Okay, that's why you need two resistors, and that can be done. And this is an L, called an L circuit, where you have bidirectional matching. And then sometimes you also see so-called pi circuits where you have 3 resistors. Then you can also control the attenuation. So here you have the attenuation that comes out is different for the two sides, and it's basically just given by the values. If you want to have a well-defined attenuation, you have to add a third resistor, and that's called a pi circuit. But that's not used very often. Okay, I think we'll take the rest to the next lecture, and this is it for today. Okay, questions? No? Okay.